A barcode system that scans barcodes and generates product IDs is a one-to-one function. Each barcode is tied to exactly one product ID. When you scan it, you always get the same ID. And also, no two different barcodes share the same product ID. That's what makes it one-to-one. Each output, product ID, comes from just one input, barcode. This function is reversible. We can build an other machine which prints a unique barcode given a product ID. Now consider a function that's not one-to-one. For example, a test that assigns grades to students. A grade of 85 could belong to 2 or 3 students. You can't reverse that process and know exactly who got the 85. So it's not reversible. With a one-to-one function, you can go both ways, forward and backward, without confusion. Every input gives one output, and every output came from only one input. If vertical lines detect whether a graph is a function, horizontal lines check if it's reversible. 1 hit per horizontal line? You're good. 2 hits? Not reversible. Inverse functions are like canceling machines. Each one undoes the effect of the other. Think of a function that encrypts a text message. It takes readable words, the input, and scrambles them into coded text, the output. Now, apply the decryption function to that coded text, and you get the original message back. That's how the canceling laws work. The encryption and decryption machines are perfect opposites. When you run one after the other, they cancel out and return to the original. The idea is, if you can go forward with a rule, and then perfectly go backward with another rule, you've got a function and its inverse. They're mathematical undo buttons for each other. Finding the inverse of a rational function is like untangling a necklace after it's been in your pocket all day. You patiently solve for x, then flip the roles. The key is, calmly move every term with x to one side and every term without x to the other side. Factor out the x and isolate it. Consider the encryption and decryption functions. Note that the output from one is the input to the other. If your encryption function takes plain text and turns it into coded text, then the decryption function must accept that exact coded output as its input to work. That's why the range of the original function becomes the domain of the inverse, and the domain of the original becomes the range of the inverse. It's a perfect swap. Whatever values the first machine sends out, the second machine expects to receive. That's what makes the two functions compatible and perfect canceling machines. This graph shows a function and its inverse as reflections over the line y equals x. Notice how the blue curve, cube, and red curve, cube root, mirror each other. There's a kind of mathematical elegance in this perfect symmetry. Each point on one curve has a matching point on the other, just with the coordinates flipped. It's not just smart, it's beautiful. The composition works cleanly in both directions. You plug one function into the other, and they cancel out perfectly like Ctrl+Z after a terrible edit in Photoshop. Sometimes a function is a bit promiscuous. It connects the same output to multiple inputs. Many-to-one relations are functions and no one is judging them. Restricting the domain is like asking it to commit to one relationship for now so we can finally define the inverse. In 1906, Sir Isaac Factorton was asked whether life had an inverse function, whether one could simply undo bad decisions and return to a previous self. He chuckled, took a sip of his cold coffee, and said, "Reversibility is a myth, unless you're a one-to-one function." The class laughed. He continued, "I have never seen anyone get away with a bad decision simply by swapping variables or even restricting the domain.